Hello and welcome to episode number 9 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode, we are going to start a new topic, which is the topic of processes. So that's all really exciting, right? But before we get started, there's just a few things that I would like to bring to your attention. First off, if you're following along with the textbook, and again, the textbook isn't required reading, it's just if you're interested, you're welcome to read it. It's a pretty good book, actually. The section that would be appropriate is the one on processes and the processes API. And please make sure that you pay attention on Piazza. We have a few updates to A1Q2 starter code. This should not impact your implementation in any way. You should be able to just copy and paste your implementation into the required functions without any issues. It's just we had a little bit of a problem, and then we fixed the problem, and then we actually fixed your problems as well, which was bad, because then we can't determine whether your code deadlocks or not, so now we had to do a couple little fixes. And our sincere apologies. One thing I would like to bring to your attention is many of you may have tried to log into the CS servers this morning and noted that you can't. Or if you can log in, you might have noted that your home directory is missing. My understanding is that there was a hydro outage last night due to the heavy rain and MC. It's pretty normal. And that may have taken out some of the computers and some of the systems there. And they're still experiencing some power fluctuations. So they've actually turned a lot of the services off until they can get the power stabilized and get everything back up and running in a safe and stable manner. So please do not panic if you can't log in. I may extend the deadline because obviously many of you are probably working on the CS servers, and this is probably going to impact your ability to do so. So I will talk to our admin and we'll talk about getting the deadline extended another couple days. And that's just because it's not fair to you to not have a place to do your work, and it's completely not your fault this time. Yeah, it's the weather's fault. Hopefully it didn't rain in MC this time. I remember when I was in undergrad, it rained in MC once, and I think that took out a good part of the server room. All right. So we'll get that sorted, and any updates I have for you, of course, regarding deadline changes and stuff, we'll post that to Piazza so that you have plenty of warning and plenty of time to adapt to that. But again, please be patient as CSCF brings things back online. That can take a little bit of time, and if you're panicking, I get it. I was running an experiment last night on the CS servers myself because I didn't want to burn my own computer out. And at this point in time, I can't actually retrieve my results, nor do I know if they actually finished. Although luckily I built a regression test into the system, so hopefully I can recover wherever it left off from. All right, so let's move on then to our OS of the day, because it's that time. We finally actually have made it to Unix, which is kind of fun. And this was developed starting around 1969, a little bit before then, to 1973. And it was a product of Bell Labs, which is a big research facility like Xerox PARC. It's just another one of these computation research facilities. And the people who actually developed Unix were the people who were working on Multics previously. One of the names is actually missing from here. So there's Dennis Ritchie, who many of you may have heard that name, and the other one is Ken Thompson. Dennis Ritchie unfortunately has passed, but Ken Thompson is still around. And Brian Kernels was also involved with some of the utilities development for the original Unix system. And you may have heard of KNR before in terms of KNR-C. So that's a fun thing. That being said, if you're ever wandering by the CS Club, if you're ever back in person before you graduate, please, please, please do not read a KNR-C book and use that to learn C and then take that and try to implement things in C. KNR-C is just another flavor of C, kind of like ANSI C. But it has some interesting quirks, language quirks, that are not really compatible with modern compilers, so be careful. It's kind of interesting to see that code because it's a different style of C, but it's not really the most compatible these days. So just be careful. So why did these Multics developers come over? Well, they decided that Multics was a bit too heavy, too complex. And if you remember, Multics had this whole system built in where they wanted you to be able to unplug and plug in pieces of hardware and have the operating system still continue to function as normal. So they really wanted to have that initial plug and play stuff, and that can actually be pretty heavy. The other thing is Multics wasn't really a portable operating system at the time, and they wanted to make something that was portable, had the features of Multics in terms of things like time sharing, but also supported multiple users, because what's the point of time sharing if you don't have multiple users back then? So that's where Unix came from. So Multics is supposed to be this multiplexed information system, and Unix is the uniplex. So it's meant to be simpler and more portable. So similarly, they treated everything as files, although they took it a degree further than Multics did, where they're literally treating everything as files. And this is something that still persists today if you're using a Linux kernel-based operating system. So you can actually communicate with devices through a file, and that's actually really neat. So like if you have something plugged into your serial port, then you can write to the file dev.tty0, and that will actually send data out over the serial port. But from your perspective, you're just interacting with the file system, and that's actually a pretty cool feature, I think. I think it's kind of neat. Even things like inter-process communication, a lot of stuff like that is just everything's treated as files. They, of course, had a hierarchical file system, but this was nothing new because other operating systems have it. I'm sure they took it a few degrees further, adding more support for various functionalities. But something else that was kind of interesting is that Unix stores everything in plain text. So there's no proprietary binaries and binary style format for each different program. Everything is just stored as plain text, which is kind of cool because you can actually open up things like a directory as like a text file, and you can see what's inside of it, and that's a really neat thing. And then another thing that Unix has that's kind of interesting is they're the first to introduce this concept of stringing smaller programs together with pipes. And now you may not understand what this means here, but if I wanted to search my list of processes and find one of those processes that's, let's say, MATLAB, I don't write one program that does that whole job. I'm going to use two different programs. I'm going to string the output of one program in as the input of the next program. So they created this idea of creating a bunch of really little programs that do really simple things, and then having the ability to pipe the output from one as the input to the next. So linking them together at like a command line. And that really stemmed from the Unix operating system. That's kind of neat. And of course, there's many other features we could go on forever. If you'd like, if you go back to the spring of 2020, we actually had Dr. Brian Kernhan virtually come in, and give a talk about his time working with the Unix developers. And so that's a spring 2020 episode you can take a look at. You're welcome to. To kind of show you the influence that Unix has had on our life today. This is actually a diagram from Wikipedia, and it is very much incomplete. It's missing so many things, but it's got all the major ones, I feel. So what you've got is the Unix original operating system at the top, which is developed on a PDP system. And then you can see here, you've got Unix 1 to 4, and then you've got BSD. Now, BSD 1 and 2 weren't actually operating systems of their own, but BSD 3 was. So if you follow the BSD chain of things stemming down from Unix 5 and 6, you can actually see that BSD turns into things like HPUX, and BSD also becomes part of AIX, and BSD also becomes... let's follow these other chains. Of course, there's FreeBSD and NetBSD and OpenBSD. And it also becomes this one called NextStep or OpenStep, which is more of a closed source version. And this one is particularly interesting because if you are running any Apple hardware, this is where you fall in the chain, because NextStep or OpenStep became Mac OS X Server, which became Mac OS X, which is what you're currently using right now. So if you are using a Mac, you are actually using a highly modified variant of BSD, which is why there's a lot of things inside of Apple that actually behave, like a regular Unix system sometimes. And then you can see here some other operating systems that have spawned off. You've got Sun, which is a closed source BSD distribution. So there's Sun OS, which eventually becomes Solaris. And then we've also got things coming out of Unix version 7, like Xenix and ScoXenix, which became ScoUnix, and then OpenServer. And I won't talk about them too much. But if you go back in time in Slashdot, SCO was in the news all the time because they were trying to sue Linux all the time. That's a long story. And then, of course, you might be thinking, well, where does Linux actually fit into this? You'll note that Linux doesn't actually stem from Unix, but Linux and Minix are both Unix-like operating systems, so they share a lot of the common ideas, and they have a lot of the same common utilities, but their kernel code is actually distinct. But there are lots of similar ideas. So Unix has had a really big influence on where we are today. And I'm guessing that at some point Windows is actually going to fall on this list, because Windows is really working. Like, they've got like a Linux kernel running within Windows now, and it's a question of how long until the Linux kernel is actually the Windows kernel. It'll be interesting to see if that ever happens. All right, so new topic then. Apologize if you can hear the fan on my computer. Computer's not very happy with me right now. That happens. All right, so we are going to start a new topic today. Maybe that's exciting for you, maybe not. And the new topic we are going to start is processes and the kernel. So we want to move beyond threading and actually talk about the programs or processes themselves. And we've kind of ignored what a process is up till this point. One of the things that I can say about this is there's kind of a debate. Do you teach processes first or do you teach threads first? And I think years ago we actually used to teach processes before threads, simply because CS342 or 343 used to actually be the required prerequisite to this course. So students were already coming in with experience with threading. But now we teach threads since that's no longer a required course or a prereq. So now we are going to come back and talk about what a process is. Now, one of the interesting things to talk about is when we've been creating all these threads, who do they belong to? Are they just random threads floating about in space? Like, oh, look, a thread, here it is. Oh, look, there's another thread. Whose threads are they? Threads actually have to belong to some program, because a thread or a group of threads are going to share an address space. Well, whose address space are they actually sharing? And the answer to that is the processes. And the process owns the threads. The threads are a part of that process. So what is the process? Now, if you go online, some people will say, oh, well, a process is just the running program or a running program. But that doesn't really capture what a process actually is and what it encapsulates. So we like to think of a process as the environment where the entire execution environment where the program is going to live and run. And if you actually look at a diagram of what a process might look like, it includes the address space, because that's something that a program needs to run. A program needs an address space because it needs the code that it's going to actually execute. And it needs the data segment, which includes, your global variables. And you might need a heap, and you need some stacks. So you need an address space for the program. And each program is going to have its own address space. So a process is going to have an address space. And then a process has an array of threads, because if you don't have any threads, and threads are the actual tool which we are going to use to execute instructions, then your program isn't going to do anything. So we can have one or more threads in our thread array. And then we have a bunch of stuff down here at the bottom of the diagram, stuff like a file descriptor table, sockets, pipes, and things like that, which are used to communicate with the file system, but also used to communicate with things like networking and so on and so forth. We're not going to go into great detail about the file descriptor table today, but we will go into that in much greater detail when we talk about file systems, because it's important to know what that is then. So this process structure, this is what a process is. It's the entire execution environment. It's everything the program needs in order to actually run. And this process structure is actually created by the kernel and managed by the kernel. And one of the things that we get from these process structures is it's going to be part of the process by which we isolate this program from everybody else. What I'd like to do is I'm going to switch over to a terminal here, and let's go into the code. Let's go over here. And so I've got to go into our code for OS 161 here. And in the kern directory, we're going to go into the include subdirectory. And inside include, so include is where you will find all of the header files for pretty much everything we need for the operating system's kernel. And we're going to open proc.h. Now my process has a few add-ons because I've obviously I've been working on various parts of the assignments. But the things that you should definitely see in the process structure is you'll see a name. Processes have a name. Now, the one thing I want to warn you about process names is that they're not necessarily unique. And we said the same thing about threads and locks. We give all of these different structures names, human readable names. But we never ever make any guarantees about their uniqueness. They're not to be used for checking whether a lock is the lock you are looking for because of that non-guarantee about the uniqueness of names. Really, these names are for the human. They're for debugging. They're not really for the system. Other ways that you can refer to a process by might be by the address of the process structure, or more commonly by something known as a process ID or PID. For the question on Twitch, is address space just a piece of memory? Yes, an address space is just a piece of memory, or it is a chunk of memory, and the process structure, as you can see here, actually contains a pointer to that address space. So there's an actual address space structure which keeps track of the layout of the address space and the size and shape of that address space, and the process structure actually has a pointer to that address space so that we can keep track of everything in it. We also, of course, have a thread array, and that is where all of the threads that belong to this process will actually live. Now we have this other stuff here called the vnode, and this is access to the file system. We're not going to worry about that, but it is also part of the process structure. We said, a file descriptor table. Well, this is a part of that. Now, my process structure has a PID field, and yours won't yet. And it's up to you to add features like that, because our process structure is very much incomplete, and through assignment 2 you are going to be completing it and actually making it work. So that is our process structure. All right. Now, before we go on to this slide here, I'd like to show you some interesting things that you can actually do in your own, outside of OS 161, but in the operating system you're using right now, to take a look at the various processes that are running and some of the different features about them. So one of the tools that you can use to do this is a little command line program, and this will work in any Unix-based operating system, called top. Now I'm going to tell you that the fields that you get for top are different on macOS than you would get on a Linux-based operating system. So just be warned, the program exists on both, but the fields are different. So if I hit top, now I hear that my fans on my computer are running at full speed, which means that my CPU is probably starting to throttle me back, which is annoying. But so I'm going to hit top, and I'm hitting top because I want to know, Who is using all of my CPU resources? Now, I knew the answer before I hit top. Excuse me. I knew it was going to be OBS. OBS is the streaming tool, that the video recording platform that I actually use. It's Open Broadcast Studio or something. It's open source software. It's great. And you can see it is using over 300% of my CPU. And that might be a head scratcher because you're like, you only have one CPU. But my CPU actually has 6 cores. So you can absolutely, when they say CPU, they really mean like things like cores. So you can absolutely have a number greater than 100% if you have a multi-core CPU. So OBS is using 3 of my 6 cores. It's using half of my computing resources right now. You can also see that it is using over 2.5 gigabytes of memory, which is expected because I'm streaming in 4K, and 4K has it's a pretty big stream. And while it is live streaming to Twitch, it's also recording to my computer, so it is using a lot of the file system. Now, what's interesting about other things that you can see here, so you can see kind of like the most active processes. You can see how much time, what percentage of the CPU they're doing, how much CPU time. You can also see the number of threads that they have. And then if you look at the very top, it tells you in total how many processes do I actually have running. So how many processes are there? How many are running? Now, what is a process that is running? A running process is a process that actually has threads executing instructions. Most of my processes are actually sleeping, and that makes sense because technically speaking, I have Chrome open, and each tab in Chrome is its own process, and I'm not actively using or interacting with any of them, so they're going to be asleep until I actually try to, mouse over and click on one of them. Now, between those 568 processes, there are 2,500 and change threads. So that's a lot. And you can see things about load averages, how much memory I have in total. I have 32 gigabytes, and you can see I am using almost all of it. That's pretty normal. I was anxiously awaiting when Apple would actually release a laptop with more than 16 gigs of RAM. Once that came out, I jumped on it immediately, but I actually wanted 64 gigs. There's no amount of RAM you can give me that I can't use. This is still a little bit too little, but it'll do for now. So this is top, and top tells us about what our processes are doing and with it. But this isn't always the most useful tool for trying to diagnose what's going on with your system. Now, one of the things I also want to say is, let's suppose you come in here and you have a program that's in an infinite loop. Then what you would do is you would look at the PID field. Every process has a unique integer, positive integer, PID. And if you come in here and you see a process that is an infinite loop, you record mentally the PID number, and then what you do is you can actually terminate that process. And to terminate the process, you use the command kill. Now, I like to do what I call kill it with fire, which means please make it dead now. And that's using the -9 flag. And then you would type the PID number. Now, I'm not going to press enter because I don't know what PID this is. But that would actually terminate the process. But maybe you didn't find the process you were looking for from top. Maybe, so this is something that I'm sure most of you have encountered in your life at some point. You traveled to an unsavory website. And a little pop-up comes up that says, you've just won a trip to somewhere. And it says, click OK or cancel. And you know that no matter which button you press, you get a virus. You can't click that button. You just can't. So what do? And the problem, of course, is that in your other tabs, you've got Learn quizzes open, you've got your assignments open, maybe you're talking with your mom, who knows? You don't want to take all of Chrome down just because one tab is going to give you a virus. You don't have to. we can actually search through all of the running processes for the specific Chrome tab processes and then try to identify which one that little pop-up is in and kill just that one. And the tool to do that is PS, and then I'm going to use the flags AX, and now I'm going to use one of those pipes I talked about. I'm going to pipe this into grep because I only want the Chrome processes. And there we go. These are all of the Chrome processes. Now, I'm actually not going to terminate any of them because these are all tabs I'm actually using, and I'd be sad if I lost one. But I can tell you that the tabs that are usually nefarious in nature look funny. Now, this one I know is just an Adobe helper, and I can see that. But you see all this text that goes with each of these tabs? This is like all of the arguments that were passed to the program when it was actually started as its own process. And I can tell you that it's usually pretty obvious which one is the bad one. It will look something like this. Now, I can actually see this, and I know what this is. I can see that this is some Adobe stuff working. I do, unfortunately, have some PDFs open, and so I know what this is. But you will see a bunch of garbage and unrecognizable flags. And when you see that, it's like, oh, that's probably the tab that has the virus. So you'll make note of the PID, and then you'll use that kill-9 to terminate that particular process, and the rest of Chrome will be safe, and you won't get the virus. So PS is another tool that we use to manage and look at what processes are running. And there's so many others too. Like these are not the only ones that exist. So going back to the slides here, there are loads of different commands that we have in order to create, manage, and destroy processes. Now in OS 161, we only actually have 5 of these. But in any Linux-based operating system, in any Unix-based OS, you're going to have tons of them. So for example, you can create processes using the commands fork and execv. And the same is true for OS 161. We can destroy processes using various ways. Now, OS 161 only has the exit command, and that is kind of like thread exit. It is going to terminate the calling process. But Linux also has kill, and this exists in Unix-based OSs as well. And kill is going to terminate the process as well. But you pass to kill the PID of the process you wish to terminate. Now, there are security rules involved here. So, for example, if you log into the school servers right now, and I know you probably can't, but when you hit top, you'll actually see a bunch of processes that are not owned by you, but owned by other people. And you'll actually see their username beside the process ID. And you might be like, I don't like how that person is running a Bitcoin miner on the school servers. I'm going to kill their program. You can't. Because the program isn't yours and you don't have sudo access. So you are not capable of killing somebody else's process. Usually you can only kill processes that are yours. If you're the administrator, root, then you can kill anybody. But if you're not, you can only destroy things that you have created yourself. That being said, if you do see people mining Bitcoin on the school servers, please let CSCF know that is an improper use of the school servers. And yes, people have got caught doing it before. The problem, of course, is that people are actually trying to do the schoolwork on the school servers. So if you're mining Bitcoin on it, you are taking resources away from other people. We don't want to do that. It's okay to run research and it's okay to do projects and stuff on the school servers, but it's not okay to mine Bitcoin. Actually, true story. So I was on Canada Computer's website, and they've actually updated their warranties to say if we determine that the reason for the fault is because you were mining Bitcoin or any other cryptocurrency, we are not going to honor the warranty. computation like that is really, really hard on your system. Yeah, because it doesn't yield and it doesn't break. So it's not ever giving your computer some time out to actually cool down and, reset. So we've got the ability to kill processes and to create processes. We also, and this is interesting because processes are isolated from each other. The address space of one process, it does not overlap with the address space of another one. They are separate things, separate entities, and they're supposed to be kept separate. Because if I'm playing Red Alert 2, I don't want some things that variables that be able to change, variables in a Chrome tab. That would be really weird and bad things would happen. So, but that being said, we do have the ability to do process synchronization. And this one takes people by surprise because if processes are isolated, then why are we trying to synchronize them? Well, here's a weird idea. When we create new threads don't have the concept of parentage. Even though there is a thread which distinctly did create that other thread, that ownership or that concept of parent, this is my parent thread, doesn't really exist between threads. But it absolutely exists between processes. So we have this concept of a process can create a new process, and we'll talk about that in a minute. And then we might, as the parent process, want to wait for the child process to terminate. Now, where might that be useful? Well, if you've ever used Hadoop, which is a variant of the MapReduce system, you are actually having your map and reduce workers be separate processes. So you need the reduce workers to wait for the map workers to actually finish. So in order to do that, you need to have some synchronization between the processes. And that is what we are talking about here. So we can wait for other processes to complete. And that's going to put one process to sleep while while they are waiting for another process. And there's a lot of, rules about this. But we'll talk more about that later. Now, Linux kernel has a lot of different synchronization mechanisms. OS 161 has only one. Then we have attribute management, and this is actually something you were seeing through TOP and PS. And this is things like getting the PID, which is what the unique identifying integer for the process, and then we've got get user ID, which means who is the owner or the creator of the process. We can get the usage for memory. We can get the usage for the CPU. There's this lovely command here called nice. And when I was in undergrad, we had to run anything long with the nice command. And what nice does is it's decreasing, you can change the priority of your process. And that's, of course, going to make it easier to share with everybody else at the school. So we used to have to nice anything that would run more than like a few seconds because they wanted to make sure that we were being fair and sharing the CPUs with everybody else. These days, the CPUs are pretty good and just don't mind Bitcoin on the school servers. But nice will change priorities and things like that. Now, there's a question on Twitch. If I dunk my GPU in liquid nitrogen and mine Bitcoin for years, would it still damage it? I'm not exactly sure that dipping your GPU in liquid nitrogen wouldn't damage it, to be honest. I have seen liquid-cooled machines. I've seen some really cool ones at SIGGRAPH a few years ago. By liquid-cooled, I don't mean like a pump. Like my current research machine is a liquid-cooled machine, but it's just like it's an enclosed system. I mean the entire computer is literally dipped, like submersed in a non-conductive oil. Pretty cool, actually. Unless you have a problem and you've got to reach your hand into a tank of oil to take the parts out. It was cool looking, though. I'm not, as I said, I don't actually know if liquid nitrogen would damage the hardware or not. But stuff like a liquid cool, if you did a submersible machine, like submersed in some kind of oil, and there are oils that you can use for this, please read instructions before you ever try something like that on your own. That you can't expect that that's not going to fail after so many years. Hardware breaks down. I mean, so a true story is I had years ago, it was like a GeForce 8. it was a GeForce 8 in a laptop, and we never did anything that I want to say was abusive to the GPU, but over time, what actually happened is the heating and cooling, the rapid heating and cooling of the GPU actually ended up causing microfractures in the solder. And when you get the microfractures in the solder, the connections aren't being made properly, and so the GPU would fail. And so what we ended up having to do, I mean, Dell at that time, they found out about this problem. It was a problem with the GeForce 8s back in the day, and Dell stopped warrantying it. So I was reading online about this particular case, and what they said is, strip up all the plastic bits off your GPU and put it in the oven for 400 Fahrenheit for 15 minutes. And this probably seems like a crazy foreign idea, but what it actually did was, it's called a process called rebaking, except you're doing it at home in your own oven. It's a very standard thing that would happen, in a chip manufacturing plant, but it's a little weird to do in your home. But what it would actually do is melt the solder and put the connections back together. Did it work? Yes. It stunk my house up for about 3 days, so I wouldn't recommend you do it. Also, that's one of those last resorts. You've lost the money anyways. But yeah, I'm not sure whether liquid nitrogen would destroy the hardware on its own. But there are definitely submersible machines where you can get a bit more. But these parts, they degrade over time. Especially if you use them. Anyways, a bit sidetracked. All right. So we've got all these different process management calls. These are things that you can use to actually create, destroy, synchronize, and manage the different processes that are on your machine. Now, I know I've shown you all these Unix-based examples, but Windows actually has them too. Some of them anyways. You've got Task Manager, and Task Manager will let you see what processes are running. I don't really use Windows that often, so I don't know what's in Task Manager anymore. Let me just open it up. Yes, I have another computer sitting in front of me. Shouldn't really be a surprise. I like computers, so yes, I have many of them. Some of them are broken, though. Or I just hate typing on tablets. So if you open up Task Manager, you can go into more details. Oh, it does show you more details now. There was a time where Task Manager just showed you what processes were running, but opening that up now, I'll actually bring it in front of the camera here after I unplug it. Here it is. So if you open up Task Manager now, that looks, because it's kind of greeny. That's right. Yay, green screen. You can actually see a list of all the different processes that are running. And it can tell you, what percentage of the CPU they're using, how much memory. So they are getting much better in Windows with the Task Manager tool. And the idea is you can find the runaway process and you can terminate it from here. Now, I don't think Windows' termination utility works quite as good as Kill-9, but it works okay. And it'll show you, things like CPU performance and all those. Other lovely things. So this is not something, these kind of process management utilities, they're not unique to a Unix-based operating system. This is something that every standard OS has various levels of support for. So another question on Twitch is, back to the Chrome tab example, are tabs separate processes because the Chrome developers developed it that way? Or does Windows itself attempt to group and separate processes? No, that was actually part of the design of Chrome. That was intentional. I actually was working at Google during that time where they were developing just before they released Chrome, and having each process or each tab be its own process was actually their own design decision. And I think it came down to that behavior where if one of the tabs freezes, it shouldn't take everything out. And maybe you don't remember using the internet before Chrome, but I do. So most people used Firefox or Mozilla. And at that point in time, I think they were starting to do the separate tabs as processes as well, because obviously they have a shared origin. But if one of the tabs froze, it would take the whole thing out. And that kind of doesn't make sense, because if one website is causing, or there's an app, and it's usually like Flash or Shockwave, is causing one tab to freeze, why should that affect Gmail? Why should that affect this other thing? They're not using that. So they wanted to keep that separate so that you could actually have better management and not lose everything you were doing. So that was definitely a design decision. And then if you go back even further in time, like the first web browser I ever used was Netscape Navigator. That browser, you can only have one tab. Like there was no, so if you wanted to go to two websites at once, you actually had to open up a separate browser. But it was also Windows 3.1, so you probably didn't want to do that either. Yeah. All right. So I'd like to show you some examples of some of these different, and talk in greater detail about some of these process management calls. So in particular, let's talk about fork. This is the command that we are going to use to create a new process. And what's really interesting about fork is it actually creates a clone of the parent, which is the process that calls fork. So we are creating a new process structure. The new process structure will have its own PID and its own address space, but the contents of the address space and the threads in the thread array will be identical to the parent. So you're creating a clone of yourself. Again, the address space is separate, but the contents are identical. And the idea is at the point of fork returning, both the parent and the child will return from fork, because remember their address spaces are the same, which means the contents of the registers are the same, so they both return from fork to the exact same thing. So that's kind of a quirky behavior there. Now there is one further difference between them, and that is fork returns differently whether you are the parent or the child. So the child, fork will return 0 to, and the parent will return the child's PID. And that's so that the parent knows the identification number for its child. So if it wants to wait for its child to terminate, we can, because we know what our child's PID is. If you're going to have a child, you probably want to know the child's name so you can monitor them and stuff like that. It was kind of weird. All right. And so fork is available in OS 161, and it's also available in Linux as well. And of course, it's also available in Windows. The one thing I will say, though, is in OS 161, it's not implemented. So actually, none of these process management calls, even though they are supported by OS 161, they don't actually exist yet inside the kernel. So the user land side of things exists, but not the kernel side. And your assignment 2 goal is to actually implement all of these things. And I know you're not thinking about assignment 2 right now, you're thinking about assignment 1. We will talk about assignment 2 next week, though. So, just a heads up. So we've got fork to create a new process, and then we've got exit to terminate a process. Now, you don't explicitly need to call exit, because if you just return from, the main thread of a process, it's going to terminate the process as well. But if you actually want to terminate a process gracefully, calling exit is one way to do it. And what's neat about exit is it lets you leave behind a message to indicate to your parent something. And usually what we're communicating through the exit parameter is the reason for death. So are we terminating because we encountered an error in our execution, or are we terminating because we executed successfully and we're all done? So we can use the parameter passed to exit to pass that information back to our parent. And then we have this function called wait PID. And wait PID is used to let one process wait for another process to terminate. But there's rules. You can only wait for your children to terminate. So only a parent can only call wait PID on your children. Parents care about why their children terminated. Children do not care about their parents. If the parent died, it's because they're older. Grandparents do not care about their grandchildren. Siblings do not care about each other, and there are such things as sibling processes. Those would be processes that have the same parent. Cousins and anything like that, they don't care about each other. You can only call wait PID on your child. And you can, when you call wait PID on your child, if your child is alive, then you will go to sleep. And when your child terminates, they will wake you up. And you can retrieve that exit status code that was passed through exit to learn why did the child terminate. It's kind of like doing an autopsy on the process. Hey, why'd my child die? Oh, because they completed their job. Great, wonderful. Now I can move on with the reduce phase of my job. So these are the first three ones. Then we don't talk about get PID because it should be pretty straightforward. Get PID is like one line of code where you return the PID of the calling process. I'm going to put that in the slides. So here's a little example of using these. So we're going to, and this is pseudocode, so lots of bits and pieces are missing. We call fork. Now to the child process, RC will be 0 because it's the child. And it can't call wait PID on the parent, so we don't care who the parent is. If this is the parent process, RC will be the child's PID. And we can use the return value from fork to decide which process is going to execute which block of code. Now remember, since the address space is identical, both processes, including the new child, are going to return from fork because the return address was stored on the stack, and the stack was in the address space, and the address space was copied from parent to child. So the child process is going to get its PID, it's going to do something, and then it's going to return a value. The parent, on the other hand, is going to get its own PID, do some work, and then it's going to wait for the child to terminate. When the child terminates, if the child terminated via a call to exit, which is what this macro is checking for, then it's going to get the exit status code, which is this X value here that the child passed around. So the child will execute this, and the parent will execute this code here. Now, a question on Twitch is, do forked processes share the address space? No, they don't share the address space in OS 161. So in OS 161, the address space is a copy, but it's like a fresh copy. Now you'll notice I quantified that answer with OS 161. And that's because in operating systems like, or in kernels like the Linux kernel, there's a little trick we can do. We note that until we actually make any modifications to the address space as either the parent or the child, they could technically share it, and that would save memory and a lot of work. So in some operating systems, until you start making changes to the address space, the two processes will share them. And once you start making changes to the address space, then we would clone and separate sometimes the whole address space and sometimes just that part of the address space. So that's a really interesting question, actually. Yeah, implementation details and fun. All right. Now to talk about execv. We say this is about process creation, and it's involved with process creation, but execv doesn't actually create a new process. What execv actually does is it changes the program that the current process is actually running. So what that means is that if I have a process that's running MATLAB and I suddenly want to run Minecraft, my 6-year-old loves Minecraft, I don't want to change the process though. Execv will let me do that. And what it does is it keeps the process structure. So your process structure is still the same. Your process structure has the same PID, but we are going to destroy the address space because we're going to run a different program, and we're going to create a new address space and load the new program into it. So execv is going to change the program that the process is running by destroying and recreating the address space, and then setting the next instruction to be the entry point function for the new program. So fork and execv often get used together because you want to create a new process and have it run a different program. Now, what's really interesting about the processes is before we talked about this concept of you actually have parent-child relationships between parents and child processes. So that relationship is actually important, especially for synchronization of processes. When you use execv, the parent-child relationship doesn't change. You can dye your hair any color of the rainbow, and your parents might hate it. And they might say they're going to disown you for it. But from a biological perspective, they can't change that. They are still your parent no matter what they want to do. And the same is true with exec-v. No matter what your child process decides it's going to run, even if you don't like it, they are still your child and you cannot change that. So exec-v maintains the PID and it maintains the process structure and it maintains parent-child relationships. So a couple questions on Twitch about the previous piece of code. One is this piece of code having infinite recursion to fork new processes? No, it doesn't, actually. We are going to, because we are not running main more than once. Because the parent and the child both are going to return from this fork here. The child is going to execute only these 3 lines, and the parent is only going to execute these lines down here. So there's no infinite recursion. And yeah, so the parent, again, the child will execute these lines. And we know this because RC, which is the return value for fork, is 0 for the child. So only the child executes this and only the parent executes this. Now, the concept of infinite recursion totally exists with fork. And in fact, this is one of the earliest forms of a denial of service attack. Is actually what's known as a fork bomb. Now, there's 2 ways that you can actually create a fork bomb. The first way is to use just threads. So you have a function. Let's bring up a VI window here. My VI window is going to cause all kinds of command line errors because of a Mac update. So we could do like a thread fork bomb. So you have, some... So here's our little function, and what I can do in here is thread fork and I'm going to attach it to the current process, and then I'm going to call fun, and then L. And I could call that once, or I could, do it twice. So each thread is going to spawn 2 other threads. Okay, so that's an example of a thread fork bomb. Now, what's interesting about a thread fork bomb is that it's a little more subtle, because if you look in top and you look in the task manager, you can see this process is consuming an exponential number of resources. So you'll know something's wrong. But if you don't catch it early enough, you may not really notice it. So it's a little bit harder to detect unless you're looking carefully at the output of top. But if the nice thing about this kind of fork bomb is that it's easy to kill. Because if you kill the process, you kill the whole thing. The other kind of fork bomb is a process fork bomb. And there's actually some sample code in the user directory for OS 161 for a process fork bomb. But essentially it looks like this. Same idea, but instead of doing a thread fork, you're going to do a process fork. So you're going to just do fork, fork, fork bomb. So this process is going to spawn 2 processes, and all of those processes are going to call fork bomb. So this is also going to create an exponential number of processes. The other one created an exponential number of threads. This one is really obvious because if you look at Task Manager, you will see like 1 billion copies of fork bomb, but it is really hard to kill because the processes get created and destroyed so quickly that you can't actually kill them all. Yeah. This is an old kind of denial of service attack. And what you would do is you would actually put this in like the Windows batch file for startup. So I may have done this when I was a kid. It's kind of funny. So it would essentially bog the system down. Fun stuff. All right. So a couple more questions on Twitch here before we move on. So we have, what do I give up can I give a process up for adoption? Not in OS 161. I'm not saying that's not possible ever. Certainly you could write some code to change the parentage of a process. I don't really know why you would do that. There's no real advantage to that at this point that I can see. But I mean, it's certainly something you could write. Then there's a question, does child fork for a new child? I'm not sure what you mean by that, but it's entirely, the child didn't create a new process. Even though it returns from fork, it didn't actually create a new process itself. The reason why the new process, the child process, returns from fork is because it gets the stack contents from its parent, and its parent has the return address set to be the return address of fork. So both the parent and the child will return from fork, even though the child never executed it. Your child process can absolutely call fork and fork off its own children, and each of those processes can fork off their own children as well. So that's certainly possible. And in fact, that's what's happening in the process fork bomb, is each child process is forking off another 2 processes, and then each of those is forking off another 2, and so on and so on and so on. It's fun stuff. Exponential growth. Be careful about it, though, because if you do it wrong, you're not going to be very happy. This is actually I actually had an example of this to show you on like my actual computer, but after the first time I ran it live streaming, I realized I wouldn't be able to do it because it consumes the resources so quickly that it actually takes down everything. So, yeah, it kind of destroys the live stream to run it. Okay, I'm just filtering through the Twitch questions here. So, again, the return address of fork is different depending on whether you're the parent or the child. And when you actually implement fork, you'll be setting that up, because where the child returns from fork is different from where the parent returns to fork in terms of the implementation of fork in the kernel's code. So you are able to differentiate between which one is the parent and which one is the child, and you're going to set manually the return value up different for the parent and the child in your implementation of fork, so that the parent always gets the child's PID as the return from fork, and the child always gets 0 as the return value from fork. So that is something you'll be setting up when you actually implement fork. So like, and as I said before, the question is, if a child calls fork, does it create a new process? Yes. Child processes can call fork on their own. Anybody can call fork and create a new process. Anybody can. So you can create grandchildren, great-grandchildren, and so on and so forth. We don't keep track of that level of ancestry. So you only keep track of your parent and who your children are. You don't keep track of your grandparents and your grandchildren. That's not necessary, though. Okay. So I want to show you an example using execv. So this example just uses execv. Remember, execv keeps the process, but it changes the address space. So it changes the program we're running. So this is the program we are running to start with. And then we are going to call execv to change the program we are running. So programs usually take different arguments. So we are going to have to set up an array of arguments for that new program. And then we call execv, we pass it the path to the new program, and we pass it the arguments for the new program. Now you'll notice here that it says, if you see this, execv failed, because execv shouldn't return. If execv is successful, then the instruction that executes after execv is the first instruction of an argtest, i.e., we'll start just executing the argtest program. If execv returns, it means something went wrong, which can totally happen. We might not have had enough memory for the address space. Maybe this program doesn't exist, or maybe it's a bad path. Either way, there are possibilities for execv to fail, and if execv fails, then we return to the original program. But if execv succeeds, argtest starts running, and this program disappears. It's not there anymore. Because what's going to happen in the implementation of execv is after you've loaded the program and created the program address space, so validated that this is actually going to work, you destroy the old address space, i.e. this program here, and you set the process's new address space to be that of argtest, and then you will actually start executing argtest instead of returning from execv. Now here's the example like the one on a couple slides ago. We're going to combine the use of fork with execv. So again, we're going to pretend that we set up some arguments. Then we call fork. So we've got a parent and a child. The child executes this block here. It actually executes the execv, and now the child process is running a completely different program. The parent, on the other hand, is going to call waitPID and wait for the child to finish. Now, some people would say, well, the parent might be waiting forever because the child is running a different program. Except that's not actually what happens. Because, again, when you call execv, one of the things about the process that is preserved, aside from the PID, is the parent-child relationship. So no matter what program this process is running, the child is running, the parent can still wait for it to terminate. And this is how you would actually implement something like MapReduce, is you would have the map where, you would have a control system that would fire off a bunch of map workers, and the map workers would be running a different program than you because you're the control program. And then once the map workers have returned and terminated, then you'd fork off a bunch of reduce workers and they would be running, again, a different program than you. Now, some people like to ask at this point, well, why can't we just do threads? Why even have processes? There's pros and cons to both separating programs into multiple processes, and there's pros and cons to separating programs between multiple threads. With multiple threads, you get the advantage of the threads can actually work together because they share an address space, so they can communicate with each other. However, if one of those threads encounters an error, it probably takes the entire program out. So, pro, communication, con, and error takes the whole program out, so all threads would be terminated. Pro with multiple processes. If one of the processes encounters an error, it doesn't affect anybody else. The con, however, is it's much more complicated for the processes to actually communicate with each other. So there's goods and bads to both models here. So the question on Twitch is, student is still confused about RC being able to change values so the parent code can run. You were thinking that the code is the same for both, and it is, but the stacks are slightly different because when we implement fork, the parent, the implementation of fork, is going to know who the parent is, and it is going to return the child's PID here. And that will only go to the parent process because at that point, the parent and child will be separated. Their address spaces are separated. So the return values will be separated. So the parent will get RC returned as being the child's PID. The child process, on the other hand, and again, in our implementation of fork, we will know who the child is, and we will specifically set their stack up such that the return value for fork is 0. And it will only impact the child process because it is a separate address space and a separate stack. So in our implementation, we will keep these separate. All right, so I have a little example that might actually help you understand this a bit better. So that's totally the wrong thing. I want to go to, this is another one of the handouts that we have. And, oh, my messy folder. This, again, will be posted on Piazza. And the one I want to do is fork print. Yeah. Oh, no, that's not fork print. I think I want, no, proc fork. That's the one. I can never remember which one it is. So here we have a little pseudocode snippet here. And we want to know what will the parent print and what will the child print. So let me fire up my little writing pad here. It actually fires up pretty quickly now, which is nice. So again, this is pseudocode, so there might be some details missing, but that shouldn't be a problem. Really liking the grid paper. Grid paper's been really nice. So here's what happens. So if we look at this little snippet of code, we've got x is equal to 0, and then we're going to fork. So in parent and child, at the start, x is equal to 0 in both of them. Our C is different because we are going to be, the address spaces are separate and we're returning something different to the parent and the child. So the RC will be the child PID, and the child will have RC equal to 0. So the child process is then going to execute the following code. It's going to set x to 10. You will note that that does not impact the parent. It doesn't impact the parent because it's a different thread operating in a different address space. Their address spaces are not connected. After the point of forking, the parent or child can make whatever changes they want, and it does not impact the other processes. So the child sets x to 0, and then it's going to print. This is going to be our first printed thing. It's going to print A10. And then that's the last thing the child changes, and then it goes down and it's going to print C10. So that's what the child prints. And then if we look over in the parent doesn't execute that first block. The parent executes the else block. It's going to print BX. Now X is still 0 for the parent because the parent has not changed X. And the child's changes to X don't impact the parent because they're separate address spaces. So the parent prints B0, and then it sets X to 100. And then the parent prints C100. So you can see here how even though these two processes have the identical code segments, because of RC and because they separate from each other at the point of fork, changes made to one process do not affect the other process. So they are separate entities after the point of fork, separate address spaces. Okay. Now there's one more little example down here, which is a really fun one I like to do. Again, by the way, these are all previous midterm problems. From, those weird days a long, long time ago where you actually had to go into a room and write a paper midterm. Those are a long time ago. Hopefully we can get back to that. I mean, maybe. I don't know. It seems kind of stressful. But for now, we'll just do this. So here we go. We've got 3 forks. And what we want to know is how many processes in total does this actually end up with? So the best way to figure out how this is actually working is to actually draw what's known as a process tree. And what a process tree does is it lets us visualize the parent-child relationships between all the different processes. And we're going to label the processes, although their labels is irrelevant, and we'll label all of the edges in the tree so we know which fork created things. So we're going to call the first process proc A. And from now on, I'm just going to label them with letters because I don't want to type that much. Now, proc A calls fork, and the fork it's going to use is B. And that's going to create process B. Now, both process A and process B return from fork labeled B. So we've got this process returning from that fork and this process returning from that fork. And both of them are going to execute the next line of code, which is fork C. So now from fork C, we're going to get, I'm going to need to do some, it's so annoying. So maybe we're not going to do some scrolling. But we're going to get processes C and D. A returns from fork B, or fork C. B returns from fork C, C returns from fork C, and D returns from fork C. So all 4 of these processes are now going to call fork D. D, 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 and now all 8 of these processes return from fork labeled D. It's interesting, isn't it? But what this tree helps us to do is to visualize how the processes are being created, where the parentage is coming from, and so on and so forth. And so, if you include some exec V's in there and some different codes, you can actually trace, where does the program change and so on. So this is actually a pretty handy way of visualizing how are the processes being created and destroyed. All right. I am going to leave that here for today. So we have talked all about these different process management calls. We've talked about what they do. We have talked about how we use them on our own computers. So I hope you have a good sense of the processes API. And what we're going to talk about in our next episode is something called system calls. We're going to talk about the implementation of these process management calls because it's tricky. You might think that when you call fork, you are calling a kernel API function. You're not. Processes are not only isolated from themselves, they're also user code is isolated from the kernel. And user programs are not permitted to access any kernel data structures, and they are not permitted to call any kernel functions directly. So if they can't ask the kernel for anything, then how do they actually achieve anything? And we're going to talk about the magic that goes on to make that work in our next episode. So we will see you on Thursday, where we will talk about system calls, which is the implementation of these lovely functions we've talked about. So see you on Thursday.